So yeah, I'm going to talk about the lessons we learned while kind of trying to apply machine learning to brain imaging data, and especially in the Nilearn packages. So first, let me just start by a disclaimer. What do I mean by big data here? I mean, big data is such an overloaded term that you can decide what you want it to mean, really. So if you ask Google, they have petabytes of data, distributed storage, MapReduce framework. We're not Google. So basically, in our case, in MRI data sets, we have from a few hundred gigabytes to at most a few terabytes of data. And I suspect that's the case of a lot of people. Not that many people have data set like Google, I guess. So in this talk, I'm going to take a pragmatic approach. Like when I say big data, you just can replace it by data that doesn't fit in your RAM. So just a little bit of neuroimaging context. Basically, I'm going to talk about functional MRI. So you put people in a scanner, and what you get is like 3D volumes of brain activity, and that record at a long time, and you hope to use that for understanding the brain. Or why the large dataset matter in neuroimaging? So a few reasons. That you can do diagnosis like autism or early Alzheimer disease kind of thing, and through large-scale studies, and also you can understand the brain a little bit better if you, for example, do meta-analysis of a lot of different individual studies. So just the talk overview. So basically, I'm gonna run a script on what I call big data. So I'm going to start it now. It will finish by the end of the talk, and I can show the results. So we're going to run a multivariate analysis on HCP data, which is 2 terabytes. You can look at the example. The example script is reasonably small because I guess there's a little bit of code behind it. But you just load the data at the beginning. You have a scikit-learn-like estimator, and you fit it on the data, and at the end you have some visualization, to kind of show what it looks like. So basically, on my laptop, my hard drive is not big enough, so I just have roughly 140 gigabytes of my laptop. So that's the data I'm going to run the script on during this talk. So that's the simple script I showed, and hopefully by the end of the talk, you'll be able to visualize some results that make sense if you're a domain expert, which I'm not. There you go, and because you have to do something in between, while this is running, I'm going to show you a few Python patterns that were useful in this kind of that we learn while building Nilearn. So just an overview of what this analysis is doing. Basically, you have a PCA to reduce dimensions on individual subject. You concatenate that. You run a group PCA on that, and at the end you have an ICA to kind of isolate different sources of brain activity. And when you visualize it, if you're a domain expert, you might be able to look at this map and understand them in terms of kind of in terms of cognitive processes, for example. So I'm going to go now to the kind of useful patterns. One aspect which is very useful is caching. So basically, imagine you have some kind of pipeline, for example, pre-processing, and then you have different estimators you want to try on. You don't want to rerun the pre-processing, which is quite costly every single time. So, if there is some kind of transparent way of caching your results, that you don't have to kind of make manual modification to your scripts that I know I've done in the past, and I guess other people have done in the past, which is horrible, then this is great. Also, caching is good for performance, so you don't recompute something you've already computed once. So the way it looks in JobLib is you create a memory object, you tell it where to store the data, you kind of have a function that you want to cache, and then you use this mem.cache thing. The first time you will compute f, obviously, with the a as input, and the second time you will just go to some place where the result is stored and reload that instead of recomputing it. So obviously, to do that, you have to be able to figure out whether the function has changed, whether the inputs were the same as previously. So you have the fast input hashing with especially some optimization for NumPy arrays. There's an MD5 hash basically behind the scenes. Also, you have to be able, to kind of load and save results reasonably quickly. And for that, that's quite annoying. For that, we have this joblib dump and load, which are kind of optimized as well. A little bit, for example, you do a compression and you behind the scenes. Another thing that is in joblib is parallel computation. So the focus is on parallel computation without a big framework. So you try to solve simple problems. So which is embarrassingly parallel on a single machine, and we can decide whether we want to use multiprocessing or threading backends. The way you use it is kind of you don't have to change your code too much. So you create this parallel object. You tell it how much jobs. So basically that would be how much core you want to use on your machine, and you pass it to the iterator, and then basically it will kind of schedule, it will send this to multiple processes using the processing, and then return you the list of all the results. So for people that use Scikit-learn, basically that's the end of parameter in your Scikit-learn estimator. That's what happened behind the scenes. Is actually use a joblib which is shipped with Scikit-learn. And in this particular example of CanICA that's running, basically the first step was to compute subject PCAs, and you can parallelize that on the number of subjects. The good point of parallel, as I say, there's no like big framework. There's no dependency. Like you don't need PySMQ or something like this. And there are a few nice features, like you can share input arrays via different worker processes via mem mapping. And also, recently there was some nice addition, which is in a beta release to kind of group tasks. So if your tasks are very short, basically you're going to be dominated by just inter-process communication. So you can, when the tasks come back, you can kind of measure the task execution time, and you can decide to group them if that makes sense. And the speed up that we saw on kind of toy example were quite significant. Okay, so that was for the kind of joblib thing. Now I'm going to mention more like generic machine learning approach, and I'm going to mention one which is online learning. So, and a simple example to start with. Basically, if you had a lot of flow that you wanted to compute the mean on, like could you say, oh gosh, this is big data. How am I going to do this? This is horrible. Yeah, right. I need Hadoop or something like this. Well, you wouldn't. You would just say that's okay. I can just take one number at a time and do the running mean, and I don't need a lot of RAM. So that's the kind of idea behind online learning, is that you can learn on a few samples at a time, and it will converge towards the right result. So this is actually some work that has been ongoing in this kind of script that is running. So this is the second step, where you kind of concatenate all the subject data and you do the group PCA on that. And the first example showed, so you see like this is actually when the result from the individual subject PCA come back, and that's the kind of group PCA on that, and you see this huge memory peak. So that's on a result that's on a subset of the data where basically this fits in my cache. If you use incremental PCA, that was actually added recently in Scikit-learn, then you see that the memory usage after the individual PCA stuff is kind of constant. And the plots were obtained through a memory profiler, which I encourage you to use if you want to look at the memory usage and profiling. So just to mention some hardware aspects. So basically, by itself, we have this big machine that that a lot of the work is done on. And 300 gigabytes of RAM and a lot of problems, we can fit the data in that. And we've observed that sometimes for some of the work, it actually gets we get the job done faster than on our cluster. And there's this interesting article that I encourage you to read, where the guy looked at the kind of typical job size that was submitted to Hadoop clusters. I think it was Yahoo and Microsoft, what I remember. It basically showed that like the median size is like 10 gigabytes or something like that. So that's a bit old. So I don't know whether that's still true today. But like that was 10 gigabytes, and for this kind of problem, it showed that basically running on a single big memory server might make more sense than running on a cluster. That's 5 minutes. Okay. Cool. So, having talked about these simple Python patterns, I'm just going to talk briefly about Nilearn. And basically the best way, if you're interested by Nilearn because you're doing fMRI or because you're just curious, is to go to the Nilearn gallery example. So that's a snapshot. I can maybe show it. So there you go. So you have plenty of a few examples grouped by kind of different subtopics, and with kind of the goal is to have some nice plot that show you the end results. You have to remember that our target audience might not be very technically savvy, so it's like as simple as possible, and then some of them are kind of trying to reproduce article results like XP and this kind of thing. And you can click on that and you have the code. I mean, usual thing for this gallery example. So a recent project started that started from trying to. So every kind of project has this kind of gallery generating thing that they have and that they tweak and so there was a project recently trying to have a common tool for this, which is called Sphinx Gallery. So I was more or less starting from trying to harmonize like Scikit-learn and Nilearn. So that's ongoing, and if you want to look at it and suggest improvements, you're more welcome to do that. More than welcome to do that. At the moment, it's using Nilearn. It's still not in Scikit-learn, but we're hoping to get there at one point in the near future. So maybe just a general overview on Nilearn thing. So Nilearn is like trying to kind of make it easier for you to use Scikit-learn on new emerging data. So the way it does that is it provides like a downloader of a few open source data, so that you can, everybody can get the data from the typical kind of sources. It takes a while, so I encourage you not to try it during the conference. Maybe try it with a good connection because it's generated data like a few gigabytes. So then there's this very useful masker object, which are kind of transforming your 4D data, which is these 3D volumes of brain activity, into the standard X matrix, two-dimensional n features by n samples by n feature matrix. So that's what this masker do. And once you're there, then you just have to use the normal kind of usual, do your scikit-learn stuff, and you can use the inverse transform to map back into a brain space. And then in Nilearn, we provide a few visualization tools, simple visualization tool that kind of look in 2D at what your results look like. So I'm just going to conclude here. So basically, the point of this talk, so that was to run this script, is finished. So I process, 140 gigabytes on my laptop, like and this is the result you get, and like that was 10 minutes or something like this. So just to show that, even if your data doesn't fit in RAM, then you can process it with Python, and you can process it without using like a fancy, distributed array and MapReduce framework. And for this, then I presented a few simple Python patterns, so job limb mostly, and caching and parallel, and one of the possible approach in generic machine learning to kind of tackle big data, which is online learning. And also like Nilearn, if you're interested if you're doing neuroimaging or fMRI and you want to look at, then I'm more happy to talk about that after the talk. All right, I think that's pretty much it. More or less on time. Yeah. Do you have questions?